2017.
Hey guys, my name is Alex. Here is Yuri. We're working on advanced threat research team at Intel, and we're here to present the new presentation, Burying the System, New Vulnerabilities in Coreboot and UEFI-based system. Before we go to the presentation, I want to say thank you to the organizers of REcon. Hugo, Sam, you're awesome. REcon Brussels, awesome. Thank you very much. Today we'll present the new type of vulnerability, and in our agenda we have that small recap about the previous vulnerabilities, then introduction about memory map.io, then description about MMIO bar overlap issue, examples of this issue in UEFI firmware and Coreboot firmware, limitations, mitigations, tools, and conclusion. The recap is really important for this presentation because the vulnerability is a little bit similar to the previous one, and in many perspectives and exploitability in the modules when we found them. Like this? Okay, thank you. So what is a semi-poison pointer bug? So in x86 system, you have a couple privileged levels, and the most privileged is SMM. And there is a mechanism to communicate between the operation system and SMM mode. And it's going like that. Operation system allocate the buffer, then pass the address of the buffer through some structure, depends on the version of the firmware, and then the SMM code read that buffer, and depends on functionality, it can read or write. In ADK1 based firmware, the buffer, the address of the buffer will pass through general purpose register, RBX. In ADK2, there is a mechanism named COM-buffer, and the address of COM-buffer is passed through UEFI ACPI table. And in normal behavior, the address of this COM-buffer is somewhere controlled by the operation system. But if we point in the address back to SMM, SMM doesn't have a check, and we have arbitrary write in SMM code. Using this write primitive, we usually control the address where to write, but we not often control the data. At some of the exploits which we demonstrated previously, we write zeros. And then to make an exploit, we find the structure in CPU safe state, SM base register actually, and when we write this register, the next SMI will start executing from unprotected memory, and ring 0 attacker can control it and make a privilege escalation to the SMM code. Then this vulnerability was fixed by adding the check in SMI handlers. So SMI handler check the address is not pointing to SMM. But what if we have scenario when we have hypervisor, or for example hypervisor-based protection like VSM, or just a Hyper-V with root partition? In this case, we can point the address in general purpose register or in COM-buffer to some of the structure of the hypervisor and override it. And in this case, the untrusted guest from ring 0 make a privilege escalation to the hypervisor. The interesting fact is that even if this vulnerability is patched in the firmware and firmware is fully protected, the untrusted guest can use it to make a privilege escalation, like confused DVT attack, when there is no vulnerability, but you can still exploit and make a code execution in the hypervisor. And we demonstrated the exploit to the VSM, which basically uses some firmware vulnerability to compromise VSM and dump credentials. We made this demo in 2015. There was another example of SMI pointer vulnerability founded by ATR and then published by Sogeti ESSEC lab. The vulnerability is pretty similar that we found. So it's reading the buffer from the general purpose registry, pass the buffer to the function read flash data. And in the function read flash data, it's using the function read, and you're controlling the offset of the destination, you're controlling the source and the size. And in this case, there is no checks where the address will be, so if your address is in SMM, you can dump and read and write SMM. Really nice write-up. Also, Dmitry Alexiuk published couple blog posts about different type of SMM pointer vulnerabilities. So how the community and vendors react on this, how we fixed it. There is a protection, which I already mentioned, to check that the address not pointing to the SMRAM, and through a function SMM is buffer outside SMM valid. It fixes the problem with the firmware, but it doesn't fix the problem with the hypervisor and the vulnerability and the bypass privilege escalation to the hypervisor. So to fix this vulnerability, there was another mitigation added to the limit COM buffer address, and so address now should be fixed. And there is an ACPI table, name Windows SMM mitigation ACPI table, which is basically should be initialized by the firmware and read by the operation system, which is passing the configuration of the mitigation. And there is a couple bits there. One is defining that the common buffer is fixed and in the defined location, and the SMM is checking all of the input and output buffer. Another one is nested, that meaning that if you have a pointer inside the COM buffer, it's checking these pointers as well. And another protection is that you have locked some of the configuration of the hardware after exit boot during the exit boot services. For example, interrupt controller, IOMMU, and so on. That kind of mitigation was added after we published this research and communicate with vendors. A little bit about MMIO, because this bug is really rely on the different behavior of the MIO. In x86 system, to communicate with the device, there is PCI Express protocol, and in this protocol there is a fabrics which contain multiple components. That components interconnected to certain topologies. In this topology, there is a root complex which has multiple ports. There is endpoint switches, bridges. All of them is connected via PCI Express link. Every physical component has up to 8 virtual physical functions, and some of them may integrate to the root complex. So basically, this protocol is allowing to talk to the device and send DMA and so on. Every device has PCI config space in a device, and that PCI config space contains the header of the header, then it contains the PCI Express capability structure and the extensions. So the entire structure is 4K, but without extensions it's 256 bytes. To get the access to the PCI and PCI configuration, there is two interfaces. One is to get access to PCIe configuration space using port IO CF8 CFC. When we construct the address, knowing the bus device and function and offset which we want to read from the specific device, and then to pass it through the CF8 CFC, we can read and write to specific register in PCIe configuration. To get access to the extended configuration space, we need to use enhanced configuration access mechanism, which is implemented as memory map. So it basically memory, which is split by 4 kilobytes per each bus device function, and through that memory we can access to the extension configuration space of the device and read the registry from there. So to read them, we are using MMIO control memory map config register plus bus multiply 32 multiply 8 multiply 1K plus device multiply 8 multiply 1K plus function plus offset. Then we construct the address, then we use it as a memory access, and we can read and write registry. So there basically all of that configuration, all of that PCIe configuration is for storing some configuration registry for the device. But even 4K was not enough for modern devices. They want to store much more, like graphics want to store megabytes. And here was the era when MMIO became. So the MMIO is the range of memory, and access to that range is forwarding to the device, and device will handle that. And this ranges is defined through MMIO bars, and MMIO bars is in PCIe config space, which we are talking on previous slide. And if you see, like, there is a header of the PCIe configuration space, and there is device ID, there's a vendor ID, status registry, some other register, and then the base address 0 is the first MMIO bar. As you see here, there's just the address, so we don't know the size. The bars itself, they are self-aligned, meaning if you write all Fs to the bar, the bits which didn't flip from 0 to 1 is the bits which define the size of the MMIO bar. For example, if there is 1 byte didn't flip, then meaning that you have the 256 size of the bar, 256 byte. Here is the simplified version of the layout in the memory, just to get the small representation of where SMMIO is. So we have a low DRAM, then there is SMM protected by SMRI, so there is a graphic memory, then we have TOLUT, and there is a memory map config, then there is low DRAM with all of the bar which was defined through PCIe config space. And there is a direct map and BIOS, and there we have high DRAM. So all of the bars should be defined somewhere here. And here's a couple examples of the MMIO bars. There is the name of the bar, like GTT MMAdder, which has the address of 000210 with 10 is offset, and then it has the size, the 2 megabytes. So all of them is, you can use a chipsec tool to just run MMIO list and enumerate the known PCIe bars, MMIO bars, sorry. So one of the important aspects of the MMIO range registry, MMIO bars, is that they can be reallocatable. At runtime, and OS can reallocate them to any other location. Some of the MMIO bars is not relocatable. They are fixed or locked by the firmware, but some of them is relocated. And now Yuri will explain why it is an issue.
Hey everyone, I take it you can hear me. So I've just noticed that all of the animation that I spent hours on is pretty much gone from the slides. That's convenient. That's, I guess, the difference between PowerPoint and PowerPoint Viewer. Anyway, so how is that related to what Alex been talking about? These issues are depend on this memory mapped I/O configuration behavior. And in fact, they are kind of caused by the way firmware talks to the devices, through the memory mapped I/O. So the way firmware uses this memory mapped I/O mechanism and communicates with the devices is that, and this is specifically to the SMI handlers, but keep in mind that the entire firmware, including the boot firmware, regardless of which type of firmware that is, UEFI-based firmware or Coreboot-based firmware or just legacy BIOS or anything else, also talks to the devices through the memory mapped I/O mechanism. So there is a PCI configuration space in each device, or actually each virtual device or a function of a device, PCI config header, and it has this base address register which defines the base of the memory range for that particular device. And so what usually SMI handlers do, as well as any other firmware, boot firmware, they get the base register, they read the base register to get the base address of this SMI range, and then they either read registers within that range, MMIO registers, or write those registers, or read, modify, write those registers. So basically, in order to send I/O cycles to the particular device. And so, yeah. So this is how they essentially communicate with the devices. Now, the problem, the theory of the problem becomes that there's an implicit trust assumption on the firmware side, on the firmware part, that those are hardware registers. So therefore, they're part of the hardware, and hardware is part of the trust boundary. And so basically, firmware, for the most part, trusts all of the hardware, right, including those registers. So there's an assumption that nobody can change those registers. However, those are just ring 0 accessible registers that could be modified by any ring 0 code, right? So that's one example of what the ring 0 code, OS level code, can do, or the code, the ring 3 code, if it has enough privileges to talk to the PCI config space. Let's say modify PCI config registers like this bar register. So, the problem is that this ring 0 code or OS level code can modify those bar registers and relocate the range for a particular device somewhere else in physical addressable space. It could be somewhere in other MMIO. It could be overlapping with some other things, but it can also be in the DRAM, in the system memory. And specifically, one particular location where the attacker would be interested in is the system management mode memory. So the exploit code could modify and relocate the memory mapped I/O range to overlap with the SMRAM. Then, when SMI interrupt is generated, either by hardware or by the attack code itself, the firmware, SMI handler firmware, attempts to communicate with the device through this memory mapped I/O range, attempts to read registers or write registers. And so basically, instead of actually sending cycles to the device as MMIO cycles, which are memory cycles on the PCI bus, it sends memory transactions to its own memory or some other memory, depending on where the attack code relocated this MMIO range. So that potentially can either expose data because it reads its own memory, or basically modify the control flow somehow if it reads some attacker manipulated data, or it can potentially corrupt the memory because of the memory write cycles to the MMIO registers. So that's the theory of this problem. And what we've observed in multiple types of firmware, including UEFI and Coreboot firmware, is that the SMI handlers communicate with a lot of MMIO bars. And examples include EHCI, USB 2 bars, gigabit Ethernet LAN, root complex MMIO, that's the main MMIO for the PCHs. Or specifically the SPI registers, basically in order to communicate with the SPI flash, write to the SPI flash or read from the SPI flash. AHCI, SATA controller, MMIO, XHCI, USB 3 controller, integrated graphics device, MMIO, basically GTT, MMA, DR range for the graphics device. Or some other MMIOs, like for example, I think it's a LED controller or something. On a different bus on the specific systems. It could be more. This is what we've seen. It could be more. So there might be a specific system that has a specific SMI handler which communicates with a specific device, or maybe has some functionality specific to that system communicating with a generic device. So this is an example. This is an example of communicating with the SPI controller in order to read something from SPI flash or write something to SPI flash. So there's a command, basically. The first command is attempting to store a persistent configuration for the UEFI firmware into the SPI flash. It's called UEFI variable if you're familiar, but basically it's the configuration of the firmware. So this is the first command attempts to store something into the SPI flash, this configuration. And the second command just dumps this SPI memory map range, all the registers. I don't show all the registers here. I'm just showing the registers that I'm interested in. And so you can see that there's a SPI status and control register, which tells the status of the SPI cycle and also sends that SPI cycle on the SPI bus. There's an SPI flash address. It's the register that is programmed with the flash address on the SPI flash device. And there's also a whole bunch of registers that are programmed with the contents of what you want to write to the SPI flash, or what you want to read from the SPI flash. So in this particular case, this is the contents of that variable that I've been writing in the first command. So you can see all 42, that's B, right? So the contents of the variable was all B's. And you can see that all of these registers now contain the contents of the variable. So obviously, if we overlap this SPI MMI range with something else like the SMRAM or some other page protected, then we can cause this contents of the variables written onto that range. So how do we find this type of issue? So obviously, SMI handler is writing something to SPI bar or to any MMI bar. So it looks like to find all those problems, it's just easy as dump the contents of the MMI range, then cause the SMI, and then dump again and see which registers changed in the SMI. And now you know that the SMI handler modified those registers. Unfortunately, this is a lot more complex than that. And initially, we thought it would be very similar to identify those issues at runtime, but in reality, it's pretty complex. And the reason is because those are not memory contents. So in addition to firmware, other parties are also writing to those registers. So the hardware itself, the devices or integrated controllers or some logic in the hardware writes to those registers in pretty much any MMI bar. For example, some of the bars like graphics bars, the hardware writes to thousands of registers in the MMI range. So it's pretty difficult to actually identify which registers have been modified by the SMI code itself. So that's kind of a high level, entire flow, how we kind of solve that problem. So basically what we do is that we, for every MMI range, we dump the MMI range multiple times with a delay, let's say 20 times, and we find all of the registers that normally change without SMI handlers. So we add those registers to the list and call it a normal difference or something like that. And then we trigger SMIs or cause a function like the variable write that would trigger an SMI. And then we after every SMI, we dump that range again, see which registers have changed, and compare them with that normal difference, with the registers that normally change. If we see any new register that is not part of that normal difference, basically, we suspect that this register might have been changed in the SMI handler. So we send an SMI, the same SMI again, maybe even multiple times, to confirm that this register changes every time we send the same SMI. And even with that mechanism, there are lots of false positives, because even when we create normal difference, we don't catch all of the registers. So it happens that when you trigger an SMI, some register changes, but it's not really because of the SMI handler, but because of the device decided that at this moment I want to write to that new register. Oh, awesome. That's not the end. Yeah. So that's an example, essentially, just of running this sort of a tool that monitors the changes in the MMI bars. This particular example monitors changes in the EHCI USB bar, and you can see that then it then it created normal difference with just 2 registers normally change. Then it triggered multiple SMIs, and the first SMI, it found that 1 register, additional register changed, so it re-triggered that SMI again, and that register didn't change. It also can be a false negative as well, because the SMI handler might be flipping a bit, flipping 1, flipping back, and so on. But this is a suspect to investigate later. So this was a theory about the issues. Now I'll give you a few examples of those issues in UEFI firmware as well as in Coreboot. So we'll start with the UEFI. So how do we find those issues in the binary? Let's say we have UEFI binaries, we load them in IDA, and how do we find those? So one way of finding those type of issues is you can find places where SMI handlers or the firmware reads the contents of the base address register. And because we know their addresses, for every device we know the address of the base address register. So for example, this GB LAN MMIO bar, it has a multiple MMI ranges. One of them is so-called MMIO bar A, M bar, which is defined by the offset 10 hex. And the GB LAN device is the bus 0 device 25, also 29, I think, function 0. So if the firmware can use 2 mechanisms, as Alex described. One is the legacy mechanism through the CF8, CFC I/O ports, and one is enhanced mechanism through the memory map config space. So the first mechanism used and the address of that bar register for the first mechanism is calculated as device number left shift 11 bits plus the offset. There's also, of course, bus number left shift 15 bits, I think, and the function number. But in this case, bus 0 and function 0. So we have an address of that register, which is pretty unique in a lot of cases when it's used for with the legacy PCI config access mechanism. And when you set enable bit for the PCI config cycle, which is bit 31, then you have 8 and C8 10 for the this MMIO bar of GB LAN device. So for the second mechanism, it's calculated similarly. So you have a memory map config space divided into 4 kilobyte chunks for each bus device function, and the register is somewhere within the 4 kilobyte chunk for that particular device. And so you need to add a memory map config base address of this memory map config space, and you need to add an offset. You need to find this 4 kilobyte chunk within the memory map config space, and then you need to find the register within that 4 kilobyte chunk. So you calculate the offset to that register pretty similarly, but remember that this mechanism allows you to access all of the PCIe header, all of the 4 kilobytes of registers rather than 256 bytes of registers. So that's why you have C8 0 10 instead of C8 10 as in the previous. So you have a constant. You have this total address in memory, physical address in memory for that particular bar. Now you can identify all the places where firmware uses that bar or reads that bar. Once you do that, you can figure out if how the firmware uses that bar. Does it check that the address is somewhere else, or does it not? Right. So does it read or write to the registers in the bar? So this is the example for the GB LAN MMIO bar in the device 25. This is the first. We call it MBARA MMIO, the yellow thing, and the second. The third axis, the third constant, you can see F80C80CC. That's reading configuration register from the GB LAN config space, but it's a different register. It's a power management control status register. So the bar itself is the F80C8010. That's one of the reds. And so that's where firmware reads the actual address of the bar. And now then later on, you can see that the firmware is actually writing or reading some registers in that bar. It's not very clear on this particular screenshot, so it's better to look at it at the next screenshot. Now you can see that the firmware is using that MMI range, M-bar range, and writing some values. There's writing some register that the attacker controls, or writing some constant value, let's say this 7123, I don't know what that constant is, to the address or offset 32 decimal in this M-bar MMIO. So it's writing some values to the registers. And so this is without actually checking. So there's no check for that MMIO range, whether it's overlaps with SMRAM or whether it's overlapping with something else. So there's no checking. So basically, by modifying M-bar in the config space of that GB LAN device, you could potentially control where the SMI handler is writing data. This is another example for the USB MMIO bar, and it's pretty similar. So you calculate, oh great, I didn't actually put the actual final constant, but you can see that there's a USB base address register is read from the offset 10 hex of the EHCI MMIO controller, and then there are accesses to the offsets of that range, access to offset 20 at the bottom of the slide, where it flips the bits. It doesn't write controlled values, it just flips the bits. And this is also an example where in this assembly you don't see the actual constant, the full address in the memory map config space, because the address is calculated. But you do see an address of the memory map config space, then you see the offset of the bar register. So there are multiple kind of ways to do that. So it also helps with finding those issues. It also helps to find the actual functions that read or write configuration space. So the first function on the left, it uses the legacy PCI configuration mechanism through CF8, CFC. You can see CF8, CFC ports there. The bottom one is using extended mechanism. It uses memory map configuration access to read, write configuration registers. The right part is just an example how firmware uses that. So you can see that it writes, it reads the register B8 in device 31 and then writes some value to that register. So read, modify, write. It writes and then returns. So basically, what it's doing, it's clearing status bits most likely. So those were examples in the UEFI firmware. Let's talk about those examples in the Coreboot. By now, you probably understood that these issues are not really specific to the type of firmware used, because those issues are depending on the platform architecture. It's the firmware trying to communicate with the PCIe endpoint devices on the platform that adheres to PCIe architecture. So regardless of which type of firmware you have, Coreboot or a legacy BIOS or a UEFI-based BIOS, those issues might exist. So because we have a source code for Coreboot, and by the way, I just wanted to thank Coreboot team and Ron in particular for working with us on this. So because we have a source code for Coreboot, we can look at the source code. So in order to find those issues on Coreboot, you can do this. You can find the functions that read PCIe configuration registers, as in the previous slides, in the source code, and then you can find functions that are writing to the memory mapped IO ranges. So in particular in Coreboot, those are functions PCI read config 32, or PCI read config 16 to read the configuration registers, and then functions write 16, write 32, or read 16, read 32 in order to read or write memory mapped registers. So in this particular case, you can see that the firmware is reading the MMIO range from a integrated graphics device at offset 10 hex, and then it's writing some register to the PP control offset of that range in the graphics range with a specific value, which it's calculating before. Sometimes in the source code, obviously the developers are naming the bars with their names as they defined in the platform specs or chipset specs or SoC specs. And so, for example, on Intel systems, you can find those accesses by just most of the bars by their names, either RCBA or SPI bar, SPI MMIO or PCI-based address, and so on. So you can look up the bar register names and just essentially just grab all the source code by the names. So that's a particular example in mainboard I/O trap handler, SMI handler in Coreboot. So this SMI handler, it's not in software SMI handler, so it's not the SMI handler that you would trigger by writing some value into the B2 register I/O port. It's an SMI handler that is caused by the chipset on trapping of I/O cycle to some other port. It's called I/O trap mechanism. I won't describe in details that mechanism, but basically it's another way to trigger a lot of SMI handlers on the platforms. Probably the second most used mechanism to generate SMIs. And so what this SMI handler does, it reads a MMIO range base address from a device 0 on bus 1 at offset 18 hex. It reads the address, and then it's checking one register. It's called LVTMA BL mode level in that MMIO range. It checks whether the value is greater than 10 hex. If it is, then it tries to either decrease it. If it's less than F0, then it tries to increase it. So what it's doing is essentially it's trying to change the brightness, and you probably don't see this. Yeah, so basically when you press the button on that Coreboot system, it would generate an SMI, and depending on which button you pressed, it decreases the brightness of the screen or increases the brightness of the screen. So it does that by reading the contents of the register, incrementing or decrementing the contents of the register, and then writing it back. So basically, potentially by pressing the button, you can, and overlapping that bar with something else like SMM, you can cause the SMI handler to override itself and get the potentially memory corruption or code execution. Or the ring 0 attacker might generate that SMI on your behalf without the pressing the button. So another case is another case in Coreboot firmware is another SMI handler. It's called backlight off, which is very similar, but it's triggered when you press the power button and the system goes to S5, soft shutdown. And so SMIs are generated, the firmware takes control, it needs to turn off devices, including it wants to turn off the brightness, well, not brightness, it needs to turn off this backlight to the screen. And so I don't remember the specific system that this SMI handler was on, but basically what it's doing, it's reading a register base, the base for the MMI device, for the MMIO range of the integrated graphics device, and it also writes a different value to the same PP control register on entering S5. So potentially by entering S5, you can control the value of the offset in the memory that you overlapped, in the memory that you overlap with the graphics device MIO bar. Or the attacker in this case would need to simulate the S5 event, trigger event, and prevent the system from going actually into the S5, but still causing the SMI handler by just directly calling that SMI handler. By now you might have figured that there are lots of moving parts in this type of bugs, in this type of issues. There are limitations. The first limitation for the exploit is that the SMI handlers or any other firmware is writing to specific offsets. So you don't really fully control the address. You don't have an arbitrary write primitive. You only control the base address plus the offset. The bars, like Alex mentioned, most of the bars are self-aligned or size-aligned. So if you have a 4 kilobyte large bar, the MMI range, then it's aligned on a 4 kilobyte boundary. This is not a requirement. Most of the platforms do that. But architecturally, PCI architecture defined that the bars might be as small as 16 bytes and aligned at 16 bytes. So there might be MMI ranges that are as small as 16 bytes, and you pretty much have a fine granularity of the address that you control. But for 4 kilobyte bytes, you have quite a few possibilities to override. But for larger bars, let's say 16 kilobytes, that becomes more difficult. For bars that are even larger, like the graphics device bar, those bars are 2 megabyte large or 4 megabyte large. You have a very few possibilities. And the exploit may not be able to control the values that are written because the firmware or the SMI handlers typically write specific values or flip specific bits at those offsets, or even read a value, then modify it somehow and write, or read the value and write to some other register. So the exploit may not control the values. Although, as you saw, for some MMI ranges, the exploit might control. So, for example, in the variable write example, you saw all of the contents of the variable that you fully control. The other limitation is that because those are memory mapped I/O ranges, those are not regular memory DRAM ranges, then that means that the firmware is actually implementing a protocol in a lot of cases. So it's not just writing, like I want to write 0 to this offset. No, it usually implements some sort of protocol, and protocol could be as simple as read the value. If that value has some, if that register has a specific value, or it's greater or less than something, then write to somewhere else. That's easily controllable because you don't just relocate the bar into memory. You also create the contents in memory of all of the registers as if they were in the MMI range. So you can control that. But if the protocol is more complex, like for example, the firmware is issuing specific cycles on a specific bus, then it's typically writing to some registers, then reading back other registers, polling on the values in those registers, then writing something else. So in that case, you may not really be able to control that because you only have one chance. You populated the fake MMI range in memory, and if the firmware writes something and expects it to change, then you're out of luck because you don't have any agents running in parallel. In certain cases, that might be bypassable in platforms, but in larger cases, you're out of luck in this case. Plus, there are lots of conditions. The SMI handler will write to that bar depending on, let's say, platform mode. Are we in a CPI mode or not? Is the device I'm communicating with supporting this functionality, this mode or this feature, right? And plus, even triggering those SMIs that communicate with the devices might even cause some complications, because it's not as just you trigger SMI through writing to port B2. No, those SMI handlers that you saw might be caused when you enter S3 or exit S3, resume from S3, or when you enter a soft shutdown or something like that. So kind of a complications on how you even trigger the interrupts. So yeah, and for certain number of bars that are non-architectural, basically they're not defined in the PCI compatible space below 40 hex in the PCI header, those bars might be locked down by the firmware. So there's a mechanism in the hardware that allows you to just lock down the register, and after you lock it down until reset, nobody can change. So you cannot, for those bars, you cannot relocate them. Of course, the firmware might forget to lock them down, as we saw many times, but in that case, you can relocate even lockable bars. But if firmware doesn't forget to lock down all the bars, then you cannot relocate them to memory. You can relocate something else and overlap with the bar, but that's a different story. So what are the options to mitigate those attacks? One option is that the SMI handlers can verify that the base address of the MMI range that it read from the bar register doesn't overlap with SMRAM. That's a pretty straightforward mitigation, and it's similar to the mitigation that was done for the previous type of class of issues, the pointer bugs, and it should be done. It doesn't hurt to really check the pointer that you're not writing to your own code. But it only solves the problem partially. It prevents you from overwriting the contents of SMRAM, but it doesn't prevent you from pointing that address that you will write to something else outside of SMRAM. Let's say hypervisor protected pages or Windows 10 VBS protected pages. So in that case, the mitigation might be different. The firmware and SMI handlers might verify that the base address of the MMI range is actually in the MMIO. In the memory map that you saw from Alex's part of the presentation, it's above this top of low usable DRAM. So you can check that the bar is actually in that range and not overlapping, not pointing somewhere inside the DRAM. That's a good mitigation, although you still might be writing to somewhere you shouldn't have been able to write. So it's also partial mitigation, I think. So there is another option that the firmware and SMI handlers might do is when the system boots, the boot firmware might allocate the default range, the reserved range in the MMIO, and place all the bars there. And when the SMI handlers are invoked at runtime during the OS execution, then the SMI handler might check the value of the base address for the MMI range and check if it's within this default reserved range. If it's not, force it into the default range, it's in its default location, and use the default location. And then upon exit, just restore the value or leave it there. Depends on the firmware implementation. So in this case, you're just forcing the SMI handler runtime firmware will write to a known good location, kind of fixed location for the MMIO. And that's that particular third mitigation was done for the SPY bar example with the arbitrary constants of the variable that could be written by the exploit. So in that case, starting later, Skylake systems, I think the boot firmware allocates the range at FE01 and 4 zeros in physical addressable space for the SPI MMIO range. And so on any SMI, PCH type SMI, the chipset type SMI, the SMI handler checks that the base address of the SPI MMI range is at that address. And if it's not, then it basically overrides it with the default FE01 value. Then the SMI handler proceeds doing what it needs to do, and basically kind of preventing you from overlapping the range with anything else that you shouldn't have access to. So that's a kind of a screenshot with this example of this mitigation. First, the attacker relocates this spy bar, overlaps it with something else, just regular DRM memory, then causes the variable write that generates an SMI, and upon exit from the SMI, I'm just checking the value of the spy bar, and you can see that it actually changed to its default location. So I'll basically try to show you that on this system. You may not be able to see that on the back, but you know, you can later on you can check. So I'm reading a offset 10 hex in the device 31 function 5. That's the SPI controller on later systems. So I'm reading, and you can see it has value FE 01, 4 zeros. Ooh. Yeah. On this laptop, the keyboard is typing numbers on its own without my help. So now we'll check just the number of SMIs. You can see that 15 hex SMIs has been generated so far. Then I'm relocating the bar. Yeah. So I'm sorry, since I started showing that with the individual commands. So I'm relocating the bar to this address, which is in memory. Before the presentation, I prepared it and copied contents of the spy bar into that memory. So, okay, checking the bar again. So you can see that it relocated, now it points the SPI memory map range, now it points to DRAM. And then I'm writing contents of the variables. You can see that the write was successful, even though the SMI handler should not have access to the SPI controller in this case, because I relocated to some bogus memory. It's not a SPI MMIO range anymore, any longer. So it's already a sign that, hey, the attack didn't really succeed. Yeah. So I'm reading the contents of the bar again, and you can see that it got restored to the original location. I'm checking the value of the SMI, and you saw 15 there. Now it's 19 hex. So you got 4 SMI generated during this operation, 1 per logical CPU. And so I'm checking the contents of the bar. So MMIO dump SPI bar. And not at this address. I'll just dump it to somewhere here, SPI log. And you can see that the contents of the variable that I wrote are actually in the MMI range. So the variable that I wrote is this. It has all of the it has all of the B's. So 42 hex. So that basically shows that this laptop, this system, restores the SPI MMI range to default location, and then only then proceeds to communicate with the SPI flash device. All right, so we will have a couple of tools that can find those issues. At runtime, obviously, you can proceed with the disassembling the binaries or looking at the source code, but we will release couple of tools that will help finding those issues. So one is that just finds all of the registers that the SMI handlers writes to modify, and the other one is the one that attempts to actually relocate all the MMI ranges into memory, then fuzz SMIs and see if the memory content's changed. None of these tools are perfect. They give false positives, false negatives. So it's more of a kind of a, they need to be complemented with manual analysis. So the root causes of this type of issues is that the firmware assumes that all of the hardware is trusted, including all of the registers in the configuration registers for all the hardware devices or the entire chipset that are not modified by some malicious code, for example, lockdown. And so the firmware shouldn't assume that the contents of the base address registers are immutable, because any ring 0 code can modify most of them, and they can be relocated to anywhere in memory, including on top of the SMRAM itself. And so therefore kind of check the contents or addresses of those registers. This problem is not specific to the SMM, because the SMM, it's pretty obvious target here because there's a runtime firmware, but even the boot firmware that reads contents of some of the registers upon, let's say, resume from sleep using the boot script, or reads contents of the MMI ranges from somewhere else, like UEFI variables. It also can be tricked into using memory ranges which are not really MMI ranges, but something else, and potentially can override its own code. So the boot firmware should do the same thing as the runtime firmware. So I think that's all. We have a couple of minutes for questions. Thank you for listening.
Hello. Thanks, guys, for your talk. So you were talking about kind of with the goal in mind of getting code execution in the context of the SMI. But have you seen this type of attack utilized in a virtualized environment where if you're a guest in a hypervisor that's allowing pass-through to PCI devices, causing relocation so that you would overwrite into the host kernel or something like that to break out?
Yeah, thanks, Rich, for the question. So we haven't verified all of the hypervisors, but we have done some analysis on, let's say, VSM, and when you are in Windows 10 normal world partition, it allows you to write to the bar registers. So we have not done the full analysis of whether this can be used or cannot be used as an attack, but at least the entry points are there. And for other hypervisors, if that would be possible to use this type of attacks against the hypervisors, then that would be might be possible from administrative guests only, not from unprivileged guests.
Okay, and then one other quick question. You were talking about a lot of the behavior in the SMIs is to do a read, modify, and write. So I was just thinking, like, this vector, if you had an offset into a kernel where you would have a predictable increment of that counter, is there a way basically to block it and loop that increment in normal behavior? Does that make sense?
It does. I definitely not sure that there's a way to block it on the kernel level, but also I don't think you would attack the kernel itself with this, because in the general case you have to have an access to the PCI configuration space of the devices. So in order to relocate the memory mapped base addresses somewhere else in the memory, and that already assumes that you have write access to the PCI config space, which is ring 0 in majority of the cases. So you wouldn't use this attack to attack kernel, I guess.
Right. Well, I was thinking in the virtualized environment, but yes.
Oh, yeah, yeah, okay.
Yeah, thank you.
Yeah. On the virtualized environment, in the virtualized environment, the hypervisor might prevent, of course. The first way to prevent that is to not allow any guest, including administrative guest, not allowed to modify the base address of MIO ranges. That's the first and pretty straightforward and should be done. But you can also monitor memory with extended page tables and cause APT violations on certain events, but that would be, I guess, performance heavy.
Hi, thanks for the interesting talks. I have a question regarding the relocation of the MMI bar register that you are talking about in the last slides. You told that some new SMI handler may verify the content of the register and restore it to the original location, right? Mm-hmm. But the sort of things that I have not understood is that the hardware has designed this for a reason, that maybe some device would like to relocate the MMIO bar register for some reason of accessing the memory mapper register. And my question is, how can you recognize when it's legal to do that or it's not legal to do that? I mean, there is some way to trigger an SMI handler that is an hardware one from software.
Let me see, Andrea. You had like multiple questions in the same question. So, is it legal to modify the which software legitimately can modify the base address registers for the MI bars?
Exactly.
Generally, PCI architecture allows OS to relocate MMI ranges anytime at once. In a lot of cases, I don't think that happens often, rather than when OS just boots. But this is a PCI architectural capability, so that any operating system can relocate ranges because they need to do devices may be added, they have ranges, and so they should be able to relocate all the ranges. So I don't think there's a generic way to know where the relocation of the ranges is legal or not. Again, with the virtualized environment, you can prevent it at runtime.
Exactly. In the latest mitigation that you show in your laptop, you show that the MIO bar register has been restored, right? Mm-hmm. And what I was wondering, in that case, you can't do for each SMI handler the same things, because maybe someone needs to do legally.
Oh, okay. Yeah, I get it. So you cannot do the same mitigation for all the SMI handlers. That's your question. I think you're correct that it's not a very generic mitigation. And that's why there are like three options that the firmware should consider, and a kind of combination of those three options should be implemented, I think. But it also works for if you know, because the SMI handlers are shouldn't be installed at runtime, they should be fixed. So where each SMI handler is which device it's communicating with, which MMI range it's writing to or reading from. And in that case, it might be a relatively generic mitigation because you know that in advance. But yeah, I think it's a combination of three options that should be there.
Yes, that's exactly the question. Thank you.
Okay, thanks.
I had actually a suggestion maybe for possible additional mitigation. For some devices that should not be normally relocated by the OS, like the same SPI controller, maybe the firmware could just store the bar and not read it from the device each time.
Mm-hmm. Yep, except when you store the bar, the cache the value. Let's say OS or exploit code relocates it. You're still writing to your original value because you cached it and you're not using it, not reading from the device. But then you're not really talking to the device, right? The functionality is broken, but you don't care because this is an attack. The trouble is it's more than the functionality is broken. The exploit code might force you to read writes to the cached location, which now might be used by something else.
Okay, thanks.
So there's a potential for the issue here. That's why this option 3 is more of a you do cache that beforehand when the firmware boots, but you also force this default location into the actual registers, so you know that you are actually talking to the device as well. So yeah. All right, I think that's time for the next presenter. Yeah, thank you.